Let's start this video with this cool visual. Here's our goal, nitrogenase. Huge complexity. Then this Fox space, which that's unfortunate this guy had his last name as Fock. But anyway, many configurations there. So this is not as complicated. And we can get fairly complicated even with a single atom of carbon. Then here's the stretched H2, or the hydrogen molecule, and you notice that the electrons are associated with the individual hydrogen atoms, but one electron has an effect on the other electron. So that means that there's entanglement. With no physical connection, one changes with the other. Then we have the standard hydrogen molecule, and you notice the bonding orbital, and the hydrogens are stretched to the outside because they repel each other. And then we'll start with helium, which is much nicer to look at, and we can use the same methods that we did with the single electron configurations. Now let's move from very pretty pictures to not so pretty pictures, but we can look at some of the mathematics that goes behind all this stuff. First of all, let me quickly go through the spin business. The spins, because they are in that same radius around the helium atom, because the radius is the same, you switch electrons and you don't get any sign change there. So we need this anti-symmetry so that if the spins are opposite, this spin state is described by this expression, and it shows that if you swap the electrons 1 and 2, they swap the sign for this difference here. So that takes care of the spin. But what about the other stuff? Here's the helium Hamiltonian. You notice a little HE down here with a big H, which stands for the Hamiltonian. Before we get to this one, which looks a little more involved, let's look at the hydrogen Hamiltonian. Here's the kinetic energy term, and here's the potential energy term. Now, a lot of the coefficients and so on are left out here because it all depends on R. As R gets closer and closer, the attraction gets greater here. So for helium, which is ionized, that only has one electron, notice it's got this 2 up here rather than the 1 down there. The 2 is because it's twice as attracted because you've got a +2 charge at the center of that rather than just a 1 charge. Now, if we lump all these things together, we get the attraction of each electron trying to get to that positive nucleus. So we got each of those, plus we have this repulsion term. And notice the sign is different. It's positive. So this tends to push the radii out, whereas this will pull the radii in. Now, if we go down here and try and compare this to the hydrogen molecule, then at ground state, this would be a pretty decent picture. Here shows this bonding there between the two, and we can say that the orbitals, the molecular orbital, is going to be 1/2 of, it looks like a 1s2, a 1s2b. Now see up here, that's a 1s2. So we've kind of got a 1s2a, a 1s2b, but it's not that way all the time. Notice there's that 1/2 out in front. And then we have the 2 times a combination of a 1sa, 1sb. So all of this stuff is going on at the same time, and so the molecular Hamiltonian that we can associate with this has the kinetic energy terms, which match the helium. Now for the potential energy terms, This looks like a hydrogen, a hydrogen, a hydrogen, a hydrogen. But each one of those has a different proton center, or it's got a different electron associated with it. Then the repulsion term here, and then what the heck is this thing, this 1 over big R? Well, the big R is the radius between the two proton centers, and that's going to be a repulsion term because it's going to push these two things away. Now, let's put some energy into the H2 molecule to where the centers separate enough that we don't really see electron being shared between the two centers. So that means one electron's over here, one electron's over here. I guess it's not a molecule anymore. It's just a couple hydrogen atoms. But that's not true. It's still a hydrogen molecule. And let me show you how. We don't know if electron 1 is on the B or it's on the A. In fact, you can't distinguish between the two electrons anyway, so why are we even talking about it that way? Well, the best way to describe it is a superposition of two states, meaning that either it's electron 1, it's a 1s orbital on the A with electron 1, a 1s orbital on B with electron 2, or the other way around. And this is the state vector notation. Now, what about the spins on these things? Well, the spin is either up or down, right? So, can two of them be up, two of them be down at the same time? No, the spins have to be opposite. So, that means if I measure the spin on this one, then I absolutely know that the spin here is the opposite. If I measure spin up, then this one has to be spin down. So that means these two atoms are correlated. That spin relationship is correlated between those two, whether we talk about electron 1 or electron 2. So this is what happens in molecular orbitals, is it's not just a simple idea of looking at individual atoms, but we get into this entanglement between these two. So these two are tied together through entanglement.